Yes, gas tables by air. Right. So I will put the gas table completely in your LMS. Okay, you can download it and you can take that. Or else, if you have any existing gas table with you, you can handle it for some no issues. Right. I think we will start the class now. Go for the session now. Yes. And last class we had discussed about a few problems in isentropic flow through CD nozzles, right? We want to review some of the problems here, right? And then we had discussed about isentropic flow through CD nozzles and its performance. Right? In today's class, we are going to see about flow in constant area with friction, that is Fanno. Right? The thing is, what is meant by friction? So you know very well that friction is nothing but it was the component which is acting near to the back. It's a component or force or a resistive force which is acting opposite to the flow direction. So if we have the forward force of flow direction, so with respect to wall, you are having the frictional force which is acting in the opposite direction. It is nothing but the reaction force, right? And then what in constant area that flow with friction means here or Fanno flow, you are considering only two things. That is three things. So we are considering three things here. So it is that flow with the friction means in absence of what? Heat transfer and body force. Right? So flow in a constant area in absence of what? Heat transfer and the body force is called as Fanno flow. Okay. So the definition of Fanno flow is that what then that is we have a constant area there. In a constant area there, flow occurs with absence of work, heat transfer and the body force, but with friction is called as Fanno flow. Right? So absence of work means here you are not going to have any kind of rotary motion, so that your work is good. And then there is no addition of heat transfer into the flow, and then there is no addition of heat into the from the outside. Okay. So there is no heat transfer occurs from the surroundings or inside the duct. Okay. And then body forces are absent. Body forces means gravitational forces are absent, right? So in the absence of these three things, okay, flow occurs due to friction. Okay, that is called as Fanno flow, right? So in your left hand side and the right hand side, we will have the Fanno flow variation. In your left hand side, we just understood all the concepts, okay, and afterwards we will go for the right hand side. So in the left hand side, you are having this subsonic region, right? And then supersonic region, right? So you have subsonic region and the supersonic region, right? What it determines is, for subsonic flow, I am considering a constant area, right? Here your flow is said to be subsonic initially, and at the end of the duct it becomes solid. But here in supersonic flow, initially you are having supersonic flow initially, and at the outside of the duct you will obtain the solid. So this is due to friction. Okay. So you have a constant area duct, but the flow is due to friction. Means what happens? Your subsonic flow is increasing. Okay, subsonic flow is increasing to sonic state, but for supersonic flow, when friction happens, okay, so during supersonic flow, it decelerates and it becomes into sonic. So technically, what we have is that thermodynamic definition is irreversible acceleration due to pressure. So there is an irreversible acceleration in subsonic due to pressure drop, and then here irreversible deceleration due to pressure rise, right? So you have irreversible acceleration and irreversible deceleration due to pressure drop and then due to pressure rise. So your pressure is getting increased. So this is said to be the hypothesis, right? That is your supersonic flow. In supersonic flow, whenever you have the flow at high speed, when it is entering into the friction tank, okay, what happens? The absence of work or heat transfer or body force, what it becomes actually. So the flows are completely turned to deceleration state. That is, pressure is going to be increased. Right? If you have the sudden supersonic flow, which meets the duct with a duct length of L max for subsonic and supersonic. At the constant area duct be L max, right? So in both the cases, we are experiencing the irreversible process. So as per the energy state in the state equation, that is H naught is equal to H plus C square by 2. Here I am considering velocity as C square. Okay, C for your notation for variation of flow properties. We are just changing the notation of velocity as C, right? So your H naught is equal to, that is your total enthalpy of the state is nothing but, that is total enthalpy of the pipe is said to be constant, which is nothing but static enthalpy plus dynamic enthalpy. So this dynamic enthalpy will be C square by 2, right? So everybody knows it. This is your energy equation, right? So what will be the total energy equation? That is, you are considering the mass flow rate of the duct. So mass flow rate of the duct is equal to rho is, where this mass flow rate becomes as m dot by A is equal to rho C. So we are generally call it as G, right? So G is nothing but mass density. Okay, so G is nothing but mass density. So this mass density is given by this notation rho C, and here you are going to change this rho C is equal to G, and then C is equal to G by, right? So mass density by density of the flow is said to be called as velocity of the flow. On substituting this value in equation 1, what we have? So our total enthalpy becomes as H plus T square by 2 rho square. Okay, so your total enthalpy for the Fanno flow is said to be H plus G square by 2 rho square. So your G and rho for subsonic flow, it is said to be constant. That is, your value of rho is said to be constant for an subsonic flow. Okay, but what happens due to the pressure drop? What happens? Density drops. So what happens to the enthalpy? So your enthalpy increases for this. So your H is going to increases for this state, but this enthalpy is going to affect by means of density. So when your pressure drops, your density is increasing. Okay, so when pressure drops, your density increases. So that what happens to the flow? Your total enthalpy is going to decrease. So when your total enthalpy decreases, what happens? It reaches the state F. So here, in this diagram, you are considering A to F. So this A to F process is irreversible acceleration due to pressure drop, where only thing your G is going to affect here, right? So your rho C is going to affect here. So what happens? Your rho term is getting decreases. Rho term is getting increases due to the state of variation, that is due to the state of friction. So as rho increases, what happens? Your pressure drop increases. So as pressure drop increases, what happens? From A to F, you experiences acceleration. That is, flow experiences from subsonic state to sonic state. Your F is nothing but M is equal to 1. See here, M is equal to 1. And then in BF, okay, now you are considering the other curve, BF, where you have the supersonic flow. Okay, in the same constant area, when you send a supersonic flow, what happens? Your enthalpy of the state experiences irreversible deceleration, okay, due to pressure rise. So when pressure is getting increased, automatically velocity drops. So when velocity drops, your Mach number drops. So your Mach number drops from supersonic state to sonic state, right? So this is the complete representation of Fanno flow. So I think you got to understand this. So when you have the subsonic flow inside a constant area with the friction, in absence of work, heat transfer and body force, what we experience? We experience acceleration. And then for a supersonic flow, when you go for an irreversible deceleration, that is due to pressure rise, what happens? We experiences deceleration. That is, supersonic flow is converted to sonic flow. Right? So this is the complete state of Fanno flow. So in your left hand side, I had shown you a single curve with some constant pressure, right? In your right hand side, I am going to varying the pressure, right? So when I am having the high pressure value, we have the longer curve. Okay, when you are going to decrease the pressure or for a variation of density, then your value of G is going to increase. That is, here rho 1 is said to be the higher density, rho 2 is said to be lower density, rho 3 is said to be very lower density. So when density decreases, your G is going to increase, right? And then what happens to pressure? Your pressure again drops. So these are the curves which are maintained for different densities. That is, for increase in G, your curves are there, right? So this is nothing but Fanno flow, and then Fanno curve. The curve which represents the behavior of Fanno flow is said to be called as Fanno curve. And this Fanno curve is nothing but enthalpy entropy. So the entropy of the state is said to be increasing for both irreversible acceleration and irreversible deceleration. See here, from state to A to F, your entropy increases. From state to B to F, again your entropy increases. So the entropy of the state won't be changes. Your entropy of the state is still increasing, right? So this is the Fanno flow, right? Next, we are going to construct the Fanno flow equation next. So how we are going to construct the Fanno flow equation, flow with friction pressure. So let us see one by one. Next, we are going for Fanno flow equation. So this is the constant area duct I am having. So in this constant area duct, I am considering stage 1 to 2. That is, stage 1 is nothing but Mach number 1, and the stage 2 is your Mach number 2, right? So we will have the critical condition, that is sonic state for M2. So this M2 is supposed to be M star is equal to 1, right? So what happens to the critical length? So your critical length is said to be L max, right? So I am considering two critical strength here, right? So one is your two critical length here. So one is your L1 max, another one is your L2 max. So we are achieving the maximum sonic state. So from initial stage to maximum sonic state, the critical length is L1 max. And then from stage 2, okay, from stage 2, we have M2 to M star is equal to 1. That critical length is said to be L2 max. But what is your L max? So my L max is L1 max minus L2 max. That is going to be my L max, right? So your L max is nothing but we are having the state that where the supersonic flow or subsonic flow, whatever the flow we are in the left hand side, you are going to attain only the sonic state in the other side, in your right hand side. So let us considering the control volume, and then I am defining the confined part of this L max, right? So here I am considering a small control volume. Here all the terms are there. So In this control volume, the pressure, temperature, Mach number, rho, C are said to be inflow parameters, and then P plus Tp, d plus dt, m plus dm, rho by d rho, C by dc is your outflow parameters. So in this control volume, shear stress about the wall is said to be the major component, and then the control surface, the complete thing is control volume, which is a one-dimensional control volume. And then I am considering the one-dimensional control surface. The one-dimensional control surface area is about dx. Okay, it was the unit area dx, right? So we are supposed to carry this control volume, and we are going to do the differential analysis of Fanno flow equation. And from the differential flow analysis, we are going to construct the massive equation of Fanno flow equation, right? So for this, what are the equations you are going to consider, and how we are going to solve it in step by step? We are going to see in detail, right? So you know the equation that G is nothing but rho C, right? So G is equal to rho C. So here you are going to take ln on both sides, right? So on taking ln on both sides, what you get? Ln G is equal to ln rho plus ln C, right? Now you are going to differentiate this equation. So on differentiating, what you get? This G is said to be constant, so that you are having 0 on the left hand side, and in the right hand side you have d rho by rho plus dc by c, right? So dc by c, and then you are just rearranging this equation as d rho by rho is equal to minus dc by c, and then I am going to multiply by 2c and I divide by 2c on numerator and denominator on your right hand side. So what is minus 2c dc? So it is nothing but dc square. So differentiation of c square is nothing but 2c dc, right? So just I am bringing this differentiation of c square into this, and then we have 2c square in the denominator, right? So this is your 0 by rho, and let it be equation number 1, right? And then we are going for first one, that is G is equal to rho C. That is your mass density equation, and you had derived this function, right? Differential function, that how the density is getting varied within the, okay, it is given by this equation. And then we are going to construct another differential equation, that is from P is equal to rho R, right? So from P is equal to rho RT, that is your adiabatic perfect gas equation. P is equal to rho RT, and again you are going to take log on both sides, right? So what do you get? Ln P is equal to ln rho plus ln R plus ln P, right? And again you are going to differentiate. On differentiating, what you get? dP by P equal to d rho by L, and then this ln R is said to be constant, so it is 0. Leave it there, since R is gas constant, and differentiating ln of constant is 0, and then we have ln of T, so it was dt by T, right? So finally this equation is equation number 2, right? And then you know that M is equal to C by U. So C is nothing but, here A is nothing but root of gamma R, right? And then you are changing this equation as M square is equal to C square by gamma R, right? When you write it on ln on both sides, okay, what you get? Ln M square by M, when you are going to write this as taking ln on both sides, so we have ln M square is equal to ln C square minus ln of gamma minus ln of R and then minus ln of t, right? And this ln gamma, ln r are set to be constant. So what happens on differentiating? What you get? Tm square by m square, okay, and then dc square by c square, right? And then minus of dt by t. Since these two terms are constant, okay, on differentiating you will get 0, so that we are differentiating only the term which are varying, okay. So these are the varying term. On differentiating we are getting this equation, right? Okay, still we have to find the equations, right? So let me treat this equation as equation number 2, right? And then we are going for the another equation, that is we had solved for state equation, differential equation, and then we had gone for G equation, that is your mass density equation, the state equation, and then equation 2 is state equation, and then third one is your Mach number equation, right? So after solving this, okay, you are going for your energy equation, right? So you are going to differentiate this energy equation. So what is your energy equation? H plus T square by 2 is equal to H0. Okay, so H0 is said to be constant, right? So on differentiating this, what we get? dH plus 2C dC, right, divided by 2 is equal to 0. So this 2 and 2 is getting cancelled, right? Anyway, you have to rearrange this equation in terms of C square, and then this dH is nothing but Cp into dt. So everybody knows. And then again for bringing this into C square, okay, you are just make this equation as by 2 itself, okay. So 2 by 2. So what is 2C dC? It is nothing but dC square. So dC square divided by 2. And then you are multiplying by C square and the denominator C square. And then what is your Cp? So your Cp is gamma r divided by gamma minus 1, right? And then you are multiplying by T in the numerator and divided by T in the denominator. And then finally C square dC square divided by 2 C square is equal to 0. And then what is your gamma RT? Gamma RT is A square, right? So A square by gamma minus 1 dt by t plus C square dC square divided by 2C square is equal to 0. Right? Now in this equation, you are going to multiply by gamma minus 1 into A square. Okay, so in this equation, I am going to multiply by gamma minus 1 into A square. So the next step is multiply by gamma minus 1 divided by A square on both sides. So what will be the term now? So your first term is getting cancelled, so you have dt by t in your first term. So dt by t and then not equal to, right? And then plus gamma minus 1 divided by A square, okay, and then C square by 2C square. So C square dC square divided by 2C square, right, is equal to 0. Is equal to 0, right? Now in this, what is your C square by A square? It is M square, right? So dt by t plus gamma minus 1 divided by 2 M square, right? So dC square by C square is equal to 0, right? And then what is your dt by t now? Dt by t is equal to minus of gamma minus 1 divided by 2 M square dC square by C square. Okay, so this is your dt by t equation, right? And let me treat this equation as equation number 4. Right now, what I am going to construct is that I am going to find all the variations of parameters, that is temperature, differential equation of temperature, differential equation of density, and then differential equation of velocity and differential equation of pressure. I am going to construct all the relations in terms of function of Mach number only. In terms of function of Mach number only. So I am going to construct this equation only in terms of Mach number. So what I am going to do is I am going to substitute this equation number 4 in equation number 3, right? And then I am going to find out the dc squared by c square in terms of Mach. So on substituting 4 in 3, I am substituting equation 4 in 3. What we get? So on substitution, okay, we have third equation dm squared by m square. Okay, equal to here dc squared by c square. So what is your dc squared by c square? And then we have minus of dt by dt. Okay, so your dt by dt is again minus of. So we just add it plus gamma minus 1 divided by 2 m square dc squared by c square, right? On taking dc squared by c square common outside, right? What you get? 1 plus gamma minus 1 divided by 2 m square, right? So here you are going to consider this equation by rearranging the equation, and what we get? 1 divided by 1 plus gamma minus 1 divided by 2 m square dm square by m square, right? Okay, so this is your equation of velocity variation. Okay, so velocity variation of Fanno flow with respect to Mach number as a function of Mach number. So this is your Fanno equation. So either if you are treating the flow as a subsonic flow, you have acceleration. You will obtain from this equation only. Whether your flow is said to be supersonic, again you are having deceleration. This deceleration can be represented by this equation, right? So as a function of Mach number, we are constructing all the differential equations. So you have find the dc squared by c square, that is equation number 5, right? So similarly, you have to construct all the remaining variables. So you have equation number 4 here, right? So in this equation number 4, you have dc squared by c square. Just substitute this value here and find the value of dt by t square, that is dt by t. So if you know the value of dt by t, okay, here you have d rho by rho, right? And initially we have d rho by rho. So you can find minus of dc squared by c square. You know the value of dc squared by c square, that is equation number 5. You can substitute the value here, and you should be able to find the value of 0 by rho, that is as a function of Mach number. And then you know the value of dt by t as a function of Mach number. So on substituting both d rho by rho and dt by t in this equation number 2, and you could be able to find the value of dp by t, right? And then we are also going for p naught by p relation. So for p naught by p relation, again you are going to differentiate that relation, and then you are going to substitute all the values in the equation, and you are going to find the value of dp naught by p naught, that is total pressure variation, right? So next we can go for substitution process now. So you have to change all the flow parameter variation with respect to function of Mach number. Okay, so you are going to equate all the differential terms of flow properties with respect to changes in Mach number, differential Mach number, right? So you have equation number 5. Now you are going to substitute this equation number 5 in 4. So substitute 5 in 4, what will you get? Substitute equation 5 in 4, what we get? So you have dt by t, right? So this is nothing but minus of gamma minus 1 divided by 2 m square. So minus of gamma minus 1 divided by 2 m square, right? And then here you have dc squared by c square. So instead of dc squared by c square, you are going to include this equation. So what do you get? Divided by 1 plus gamma minus 1 divided by 2 m square. 1 plus gamma minus 1 divided by 2 m square, right? And then we have dm square by m square. Yes, we have dm square by m square. So this is your equation for dt by t. Yeah, we can cancel m square, but it is not good. So we can have this dt by t equation, right? So this is said to be your equation number 6, right? And then I had been told you that we can also substitute this dc square by c square in equation number 1, right? So in order to find the value of 0 by rho, right? So substitute equation number 5 in 1, right? So what we get 0 by rho, right? 0 by rho is equal to, we have already minus of, okay, so minus of 1 divided by 2 into 1 plus gamma minus 1 divided by 2 m square dm square by m square, right? So that is your d rho by rho, right? So it was minus of 1 by 2 dc square by c square, right? So minus of 1 by 2, right? Minus of 1 by 2 I had put, and then your dc square by c square equation is this equation number 5. I had just substituted, and I had treated this equation as equation number 7, right? So we obtained equation number 6 and 7, and we are going to substitute this equation number 6 and 7 in equation number 2, right? So what is your equation number 2? dp by t is equal to d rho by rho plus dt by t, right? So substitute, just you are going to add these two terms, right? So substitute equation number 6 and 7 in equation 2, right? So therefore what is your dp by p, right? So minus of gamma minus 1 m square divided by 2 into 1 plus gamma minus 1 divided by 2 m square, right? dm square by m square, right? And then this is minus of 1 divided by 2 into 1 plus gamma minus 1 divided by 2 m square dm square by m square, right? So I'm taking this LCM term, 2 into 1 plus gamma minus 1 divided by 2 m square, right? And we have dm square by m square, right? Okay. So what we have finally, right? So on simplifying this, okay, we have gamma minus of gamma minus 1 into m square, okay? We just multiply this value with this equation. So what we get? Right? So we have taken minus of minus, we have minus term, we just take common outside, so 1 plus gamma minus 1 m square, right? So minus of 1 plus gamma minus 1 into m square. On taking minus common outside, we are getting this equation, and this equation is said to be called as change in pressure across the board equation. That is equation number 8, right? Now we are going to find P naught by P relation, right? That is, we are going to find the total pressure variation. So we had estimated density variation, temperature variation, pressure variation inside the duct due to friction, and you had derived all the equations in terms of function of Mach number. So changes with respect to Mach number only, right? Since it is very easy to solve. With respect to friction, the Mach number is getting varied, so that we are going to solve all the flow parameters in terms of temperature, in terms of density, in terms of pressure, right? And then we have to estimate what total pressure. So what is your total pressure? Your P naught, right? You are going to use this relation. So using isentropic relation, What is your isentropic relation? P naught by T is equal to 1 plus gamma minus 1 divided by 2 m square whole to the power of gamma by gamma minus 1. Okay, everybody knows this equation. Now you are going to take ln on both sides. Okay, you are going to use this equation and you are going to take ln on both sides. So taking ln on both sides. Right, so ln P naught minus ln P is equal to, okay. And we have gamma by gamma minus 1. We just in this term, power term on the multiplication, and then ln of 1 plus gamma minus 1 divided by 2 m square. Okay, so next we are going to differentiate. So on differentiating, what we get? So dP naught by P naught minus of dP by P equal to this gamma minus 1 remains there, and then differentiating of this on triangle. So 1 plus gamma minus 1 divided by 2 m square. Again the same term will be completed. 1 plus gamma minus 1 divided by 2. And then you are going to differentiate this in the term. So differentiation of 1 is 0, and then differentiation of this term, that is you are going to differentiate with respect to only m square, right? So we are going to have only this constant term, and then dm square. Okay, and then you are going to multiply by m square by m square, multiplying by m square and divided by m square on the same side, right? And then we have dP naught by P is equal to, here minus of dP by P is going to be right hand side, so we have plus dP by P, then gamma by gamma. So on differentiating this, what we get? So gamma minus 1 divided by 2, right? And then differentiation of m square, right? Whole divided by 1 plus gamma minus 1 divided by 2. So here I am going to multiply m square by m square. So in order to have the uniformity, that is dm square by m square, that is Mach number variation, so that we are going for this, right? And then here gamma minus 1, both are constant. So what we finally have, right? And then dP naught by P naught is equal to, we have dP by P, just substitute. So what is your dP by P? This is theta, that is equation number 8. So minus of 1 plus gamma minus 1 m square. Sorry for the disturbance. Welcome. We will go for the step now. So minus of 1 plus gamma minus 1 divided into m square. So we have dm square by m square. Okay, then divided by 2. So divided by 2 into 1 plus gamma minus 1 divided by m square. And then we have dm square by m square. Here is also we are having right hand side of dm square by m square. and then plus we have gamma n square. Gamma n square. So divided by 2 into 1 plus gamma dimension 0 to 2. Okay, so that common we have Pm square. So finally we have the LCM part. Now you go ahead for multiplication. Right? So 2 into 1 plus gamma dimension 0 to 2. So Pm square by square. Okay. And then we just simplify the inner term, -1, right? So -1, and then minus of gamma n square, and then minus into minus plus n square, and then plus gamma n square. Okay, taking LCM we are having this. So here plus term and minus term is getting cancelled. So what you get? I'm taking minus common outside. We have -1 plus n square. Okay, I'm taking common outside. What we get? 1 minus n square. So minus of 1 minus n square divided by 2 into 1 plus gamma minus 1 divided by n square Pm square by n square. So this is your total pressure variation throughout the right. So let it be treat this equations right. So when we find the value of total pressure, likewise we are going to find the value of force. So force is nothing but impulse. So force is nothing but how much is the amount of mass flow rate has been discharged with respect to pressure, right? So the pressure along the line, or else the total force which, that is the quantity of flow which is forcible in coming in. So the quantity of flow which is forcible that are coming in, that is called as impulse, right? So we are calculating that impulse now. What is your impulse? That is total force. Total force due to pressure, and then force due to mass flow, right? So rho A C square. So rho A C square is nothing but force due to mass flow rate, and then force due to pressure. Okay. So the sum of two forces is called as impulse, right? So in this we have rho C square, right? I'm going to change this term as P by RT. You know that P is equal to rho of T, so that P instead of rho I'm going to write this as P by RT multiplied by C square, right? What is your C square? Your C is nothing but m by root of gamma, right? And then what is your C square? M squared by, sorry, it is m is equal to C by root of gamma, right? And then what is your C square? So C square is equal to m square gamma, right? So your RT is getting cancelled. So what we get? Gamma P m square. So what is your rho C square now? Rho C square is gamma P m square, right? Just you are going to replace rho C square as gamma P m square, right? And this PA, you have PA common, just take PA. So I'm taking common out, what we get? So 1 plus gamma. So this is your impulse. Sir, what is the difference between a shock and the impulse? Impulse is nothing but a force, okay? But a shock wave is nothing but the thermodynamic behavior of fluid changes. That is, the fluid properties is getting heated up and it forms a barrier, okay? It forms a barrier. So due to all the high speed flows, we have all the high speed flows, we need the sudden obstruction. So on the sudden obstructions, the formation of air is occurring. But the impulse is nothing but the force that we are going to calculate. Okay, so we have specific impulse and impulse. We are considering specific impulse. So the quantity of fuel that has been delivered, okay, that has been required to discharge the amount of thrust, that is specific impulse, right? So impulse is nothing but a force, right? I think break mark at this point, okay, and then right now you are going to make the differential equation for this impulse in terms of m square, right? So it's very simple, that taking ln on both sides. So on taking ln on both sides, what is it? Ln f, ln p, ln u, and ln n plus gamma m square. Okay. So together we are going to differentiate. So on differentiating, what we get? So it is nothing but df by f is equal to dt by t, and the area is constant area, right? So on differentiating ln f, we are getting 0. Then on differentiating this term, okay, what we get? Differentiation of 1 plus gamma m square divided by 1 plus gamma m square, right? Now you are going to change this term as dt by t plus, on differentiating this particle, only gamma m square, so dm square divided by 1 plus gamma m square divided by m square, right? So actually we get this equation, right? So gamma dm square, and here I am going to multiply divided by m square in order to get the equality of the function, right? So what is your dp by t? So you know the value of dp by t, that already estimated the value of dp by t. This equation, going to substitute this equation, right? And then we are going to take LCM and we are going to simplify this expression, right? So what is your dp by t? Minus of 1 plus gamma minus 1 m square, minus of 1 plus gamma minus 1 m square divided by 2 into plus gamma minus 1 divided by 2 m square, okay, plus gamma m square plus gamma m square. So on the whole we have dm square by m square, okay. So now we are going to simplify this term, right? So just you are going to cross multiply, you are going to simplify this expression. So I am going to straight away multiply this term. Gamma m square minus m square, okay. So it is very easy to multiply, and we can have this simple relation one time. And then we have a gamma minus 1 divided by 2 m square, okay. Then here is also we can have the operation straight away. So minus of, so here we have 1 plus gamma m square plus gamma m square plus gamma square 10 power 4, right? And then minus m square plus gamma n power 4, right? So we had completed this cross multiplication part, okay. We have to complete this now. So here we have gamma m square, just multiply this value of gamma m square directly, so 2 gamma m square, right? And then we have another one, gamma minus 1 divided by 2. So for this expression we have 2 plus gamma minus 1 into m square, right? So separately writing it as 2 plus gamma m square minus m square, okay. This is your denominator, you are multiplying with gamma m square. Okay, so what we get 2 gamma m square, and then plus gamma m square, right? So gamma square m power 4. Okay. Then we have minus of gamma m power 4, right? So this is your numerator part divided by your denominator part. So into 2 into 1 plus gamma m square into 1 plus gamma minus 1 divided by 2 m square. Okay, so dm square by m square. Now we are going to find the impulse, changing impulse. So differential equation of impulse with respect to mass number. So here 2m square minus 2m square plus 2 gamma m square is getting cancelled, and then minus gamma square m power 4 plus gamma square m power 4 is getting cancelled, and then minus gamma m power 4 in this term is getting cancelled, right? So what we have the final term. Okay, so final term is here minus m square minus 1. Okay, we have m square minus 1 the numerator. So what we get is we have df by f is equal to minus of 1 minus m square. Okay, that is the term we are having. So minus of 1 minus m square, okay, divided by 2 into 1 plus gamma m square minus gamma minus 1 divided by 2 m square, right? And then dm square by. So this is your force equation. Sir, important question, please. Sriram, Karthik Sriram, there is no, don't worry about this. Okay. The question bank will be shared to you, okay, within today itself. Okay. You can refer the question bank in the LMS itself. Right? No issues. That you definitely receive the question banks, and that question bank will help you much more to bring out for your preparation, right? It will help you for your preparation. Total. For sharing shortly. So in your LMS, I am going to share gas tables and your question bank. So your question bank and the gas tables by Jaya. Will be shared. Right? Sir, why 1 minus gamma minus 1 divided by 2 sums is sir, sums is enough, no sir, because internal choices are there. I can't understand for a second. Could you send me again with the details? We had discussed, we had covered the first 2 units and its problems. Yeah, for long answers, problems are enough. We had consulted all the tutorial problems in the class itself. You just prepare the problem. Don't go anywhere apart from them. You just prepare the book. Follow the for problems. You may follow gas techniques by Radhakrishnan. It's good in that problem. Okay, he simplifies all the shock wave problems. That is your unit 2. You have oblique shock and normal shock. All the problems have been solved in that book. Okay, and then we have discussed all the tutorial problems relevant to your examination part. So that is also available to you. So don't worry about it. So on the same kind of problems, we ask in the question bank also. You can follow your question bank, right? Okay, students, it's time up. We have to end the meeting now. Take a break. Yeah, thank you for a second. Take a break, and we'll start the class. We will go for next class. We will meet in next class. Right? So thank you all students.